Dr. S. Nagan. He is an associate professor in civil engineering at Tyagarajar College of Engineering, Madurai. He pursued his undergraduate and postgraduate studies from Tyagarajar College of Engineering and completed his PhD at the Madurai Kamarajar University. He has more than 20 years of teaching and research experience. He has worked in many prestigious institutions including PSNA, College of Engineering and Technology, Dindigul. He has published more than 25 research papers and 5 books under his name. Apart from all this, he is a life member at the International Society for Environmental Protection and also at the Indian Society for Technical Education. To add to all of this, he is won the Best Staff Advisor at the ISTE Students Chapter.
Welcome to UGC lecture series for Bachelor of Architecture. In this lecture, we will be focusing on columns by Rankin's formula, and then we will have introduction to indeterminate beams, and this comes under unit 4 and 5 of the Mechanics of Structures 2. We have already studied the Euler's formula for calculating the critical load or buckling load, and now we will see how to apply or use Rankin's formula to calculate the crippling load or buckling load, and then subsequent to that we will see introduction to indeterminate beams. So, Rankin has evaluated formula for computing the load that can be carried by a column as sigma c into capital A by 1 plus small a into L effective by k whole squared, L effective by k whole squared. So, we will define the terms, or we will see what are the terms to find, say if you are interested in calculating the critical load by Rankin's formula, we need to be familiarized with the factors involved. Say sigma c is the crushing stress of the column material. Say the columns may be made up of steel, concrete or composite materials. So, the crushing stress of the material of the column becomes essential to compute the critical load by using Rankin's formula, whereas Euler's formula did not involve that this crushing stress value and all. And then capital A is the area of cross section of the column. So, if we are given a rectangle, we know area equal to B into D. If we are given a hollow circular section, then pi by 4 into d squared minus d squared. If it is a circular column, we can calculate by pi d squared by 4, and if it is a compound section, say if it is a T section or if it is an I section, then we know how to compute the area of the compound sections. Say compound section comprises several rectangles. So, area of each rectangle will give you the sum of capital A, and then small a in the denominator, it represents the Rankin's constant. The Rankin's constant will also be given in the problem, which depends on the material of the column, and if it is not given, we can compute using the formula sigma c by pi squared E, where sigma c we have already defined as crushing stress of the material. So, sigma c by pi squared E will help finding the Rankin's constant, and then L effective. So, effective length we need to make use of depending on the end conditions of the column. We have reviewed already what are the different effective length case. When both ends are hinged, L effective equal to L by 2. When one end is fixed and other end is free, L effective equal to 2 times L, and when one end is fixed and other end is hinged, L effective equal to L by root 2. So, with this idea or knowledge, we will now see a problem. And one more factor which is left out in this formula is L effective by k. K is the least radius of gyration. So, what is radius of gyration? That is more important. Say you know or we know what is moment of inertia. Say if we take a rectangle. So, for a rectangle, the moment of inertia I x x equal to b d cube by 12. Similarly, I y y will be equal to d b cube by 12. Say if I am going to replace this rectangle by a small strip at a distance, some distance from the x axis, then at what distance should I keep this strip, so that I will get the same moment of inertia for this strip as well for the rectangle. So, that will decide the distance, or that is called the radius of gyration. So, radius of gyration is defined as the distance at which a equivalent strip should be placed to get the same moment of inertia. Similarly, the radius of gyration, this is with respect to x axis. In a similar way, a rectangle section can be replaced by a equivalent strip at some distance from y axis. So, that we call as radius of gyration with respect to y axis. And since we know that area into square of distance will give moment of inertia parallel using the perpendicular axis or parallel axis theorem, using the parallel axis theorem, then we can find the radius of gyration using the formula square root of I x x by a or square root of I y y by a, whichever is minimum, because we are interested in minimum radius of gyration. So, if I want to find the value of k, then again this I value computation of moment of inertia becomes essential. So, we should be familiar in computing moment of inertia of different sections, which we have already studied in several units or topics. So, this is the problem wherein we will be comparing the crippling load by Euler's formula as well Rankine's formula, so that we can have an idea of both the formula. So, the problem is determine the Euler's crippling load for a cylindrical steel column of 38 mm external diameter. So, it is a hollow steel column. So, the diameter, external diameter is 38 mm and 2.5 mm thick. So, the thickness is 2.5 mm. The length of the column is 2.3 meters and hinged at both the ends, and Young's modulus is 205 GPa. GPa means gigapascal, and then we need to determine the crippling load by Rankine's formula also, using constants as 335 MPa and 1 by 7500. This is the problem wherein we can use both the Rankine's formula as well the Euler's formula, and will be comparing the results. First, we will calculate by Euler's formula. So, Euler's formula is pi squared E I by L effective whole squared. Young's modulus is 205 GPa, that converted into Newton per mm squared, you will get 2.05 into 10 power 5 Newton per millimeter squared, and I value being a hollow circular section, the moment of inertia is pi into d naught power 4 minus d I power 4 by 64. The outer diameter is 38 mm and we have been given the thickness. So, the inner diameter will be the outer diameter minus 2 times the thickness. So, it will be 33 mm, and hence moment of inertia will be equal to pi into 38 power 4 minus 33 power 4 by 64, which will have 44,117.74 millimeter power 4, and effective length we have been given E value, we have calculated I value and effective length. The effective length of the column will be L itself, because both ends are hinged. So, 2.3 meters is the given length. So, same will be the effective length 2300 mm, since both ends are hinged. So, substituting we will be getting the value of the critical load, and now we will use the Rankine's crippling load. So, because this is the thing which we are going to learn new, since we already are familiar with the Euler's crippling load, that will give some value. Now, crippling load by Rankine's formula will get a value. So, sigma c into A by 1 plus small a L effective by k whole squared. The sigma c and small a are defined in, are given in the problem. So, if you notice the problem, they are given the using Rankine's constant as 335 MPa and 1 by 7500. So, this 335 MPa is the crushing stress sigma c, and 1 by 7500 is the Rankine's constant small a. So, sigma c equal to 335 MPa, that is 335 Newton per mm squared, and A, capital A equal to area. So, pi into d naught power squared minus d I squared by 4. So, outer diameter and inner diameter are known. So, we can calculate the area capital A, and small a is given as 1 by 7500. effective length is 2.3 meter itself, because both ends are hinged, and now we need to calculate the radius of gyration k, small k. So, small k equal to square root of I x x by a or I y y by a, whichever is minimum, and in this case it is a hollow circular section. So, I x x will be equal to I y y, therefore, k equal to root of I by a, where I equal to pi into d o power 4 minus d I power 4 by 64, and area we have computed. So, using which we can find the radius of gyration as 12.58 mm. So, when substituted, you will get the crippling load by Rankine's formula as 17,108 Newton, which will be 17.11 kilonewton. So, you can compare this value with the value obtained with Euler's formula and have an idea. With this, we come to an end of the theory of long columns and short columns. Now, we will enter into the fifth unit, namely on indeterminate beams, introduction to indeterminate beams. So, first we should be in a position to know what is a determinate structure, then only you will be able to define indeterminacy. What is a determinate structure? Say, we normally use the basic static equations of equilibrium, the static equations of equilibrium. So, the three static equations of equilibrium are sigma v equal to 0, sigma h equal to 0, and sigma m equal to 0. These are the three static equations of equilibrium. When these static equations of equilibrium are sufficient to determine the unknown reactions or the unknown forces of a problem, then we say the structure as a determinate one. And examples of determinate structures will be a cantilever beam. Say cantilever beam is a determinate structure. A simply supported beam, say this end be hinged and this end be on rollers. So, this is a determinate structure, and we have the overhanging beams, a determinate structure. So, in all these cases, we can easily find the support reactions using the basic equations of equilibrium. So, when we are able to identify the reactions with the help of conditions of equilibrium, then we say the structure as a statically determinate one. Now, we will see what is an indeterminate structure. So, in contrary to this indeterminate structures, that is, the static equations of equilibrium alone will not be sufficient to calculate the support reactions. Say for example, let us take the case of a propped cantilever beam, a cantilever beam which is propped at the free end. So far we have seen only cantilever beams, wherein we will not have any support at the free end. Say for example, you have support at the free end. Now, say this is A and this is B. We have seen that a fixed support will offer three reactions. A fixed support will offer three reactions, one vertical reaction, one horizontal reaction, and a moment. Whereas this support we will have only RB, reaction RB. So, the equations or the unknown forces in this problem are RB, V, H and M. So, we will have to identify or find RB, V, H and M, and the available equations which we have in hand are sigma V equal to 0, sigma H equal to 0 and sigma M equal to 0. So, there are four unknowns, in the problem, and we have in hand only three equations of equilibrium or three conditions of equilibrium. Therefore, we have one reaction or one force in excess to be found. This we call as the degree of redundancy, dr. Now, we can define the degree of redundancy as, say, if I want to find degree of redundancy, that is equal to NR minus CE, number of reactions minus conditions of equilibrium. So, the number of reactions available in this propped cantilever example is 4 and conditions of equilibrium which we have is 3. Therefore, the degree of redundancy of a propped cantilever is 1. So, degree of redundancy of a propped cantilever is 1. If you have a propped cantilever, say this is A and this is B, say this is reaction at B, we will have V A, H A and M A. So, 4 unknowns are there and have 3 equations. Therefore, the propped cantilever is indeterminate to 1 degree. So, degree of redundancy is 1. Now, we will take the case of a fixed beam. We will take the case of a fixed beam. There are 2 ways of determining the degree of indeterminacy of fixed beam. One is without considering any horizontal force or the horizontal condition of equilibrium. If you not take, then we will have the vertical reaction and the moment as the unknown. So, vertical reaction and the moment as the unknown. Say the unknowns will be, say this is V A and this is V B. So, total number of unknowns and this is M A and M B, they need not be same, sometimes they may be same or they need not be same. So, there are 4 unknowns and the conditions of equilibrium, neglecting this condition sigma h equal to 0, because we are not considering horizontal reactions. So, the conditions of equilibrium will be 2, therefore, 4 minus 2 equal to 2. Therefore, a fixed beam will be statically indeterminate to 2 degrees. Fixed beam will be statically indeterminate to 2 degrees. And then we will take the case of a continuous beam, because these are all examples of indeterminate structures. A continuous beam like this, say we have V A, we have V B, V C, say A, B, C. We have, say in case of continuous beam, we will be having the moment, bending moment at A will be 0 and bending moment C will be 0, because they are free ends, and we will be having a moment at the continuous support. We will be having a moment at the continuous support. So, M B is one unknown, M B is one unknown. In addition to V A, V B and V C, we have M B as the unknown. So, number of unknowns will be 4 and we have 3 equations of equilibrium. So, 4 minus 3, that is N R minus C E. This is the formula to be used for calculating the degree of indeterminacy. So, we will be having 1. So, a 2 span continuous beam of this type, that is which is freely supported at both ends and which is continuous over the mid support, the degree of indeterminacy is 1 or degree of redundancy is 1. So, how we will be solving this excess reactions, that is the case. So, in case of indeterminate beams, we should know the concept only, the what based on which concept we will be analyzing indeterminate beams. The concept alone is sufficient, we need not work out problems in this concept. So, I will tell you how to calculate the degree of redundancy and what are the methods available to solve problems or indeterminate problems. Say for example, let us start with propped cantilever beam which is statically indeterminate to single degree. Say we have a propped cantilever, say this is A, this is B and we have R B. So, as we discussed, a propped cantilever is statically indeterminate to 1 degree or first degree, we will be treating R B as unknown, we will be treating R B as the unknown. So, as we discussed, we have excess reactions which need to be found using excess equation or extra equation. So, how do we arrive the extra equation? So, that extra equation can be arrived or derived using what are called as compatibility conditions. Compatibility conditions. So, the compatibility conditions are nothing but deflection or slope conditions. For example, we can use the deflection condition at B. We very well know that if we have a cantilever beam, it will deflect like this, there will be maximum deflection at the free end. So, how do we compute the maximum deflection we know how to compute W based on the load. If you have point load, it is W L Q by 3 E I. If you have uniformly distributed load, it is W L power 4 by 8 E I. And if we provide a support here, ultimately it should not allow for this deflection, it should not allow for the deflection. So, using that condition, using that compatibility condition, we will be arriving the value of R B. So, a small example will help. Say the method of analysis of propped cantilever will be, a propped cantilever is propped at the free end. So, first what we will be doing is we will be removing the prop and we will be analyzing the deflection due to assuming it as a cantilever beam, or we will make it as a determinate structure and we will analyze. And then say for example, let it be subjected to some load. So, arrive the deflection due to that load, and then remove the load and apply the redundant force. So, this we call as the redundant force R B, because it is the extra reaction which we call as the redundant force. Now, compare the deflection. What will be the deflection at point B when it is subjected to a load here, and what will be the deflection at B when it is subjected to an upward load of R B. Equate these two deflection values, because ultimately we need to get 0 deflection at the end B, since it is propped at the end. So, using that we can arrive the value of the unknown R B. So, once R B is known, then the problem becomes simpler. We can obtain the shear force at any required point, we can obtain the bending moment at any required point, and we can also proceed to deflection analysis. So, this is the basic concept involved in analyzing a propped cantilever. Similarly, say as I said, fixed beam is statically indeterminate to 2 degrees. So, in a fixed beam, if we are able to calculate the value of end moment M A, and if you are able to calculate the end moment M B, if you are able to calculate M A and M B, then that becomes simpler. Once we know the values of M A and M B, then the other reactions like V A, V B can be found using static equations of equilibrium, and then the problem can be solved. So, to obtain this, we will be again using the compatibility condition, and the equations which we will be using for fixed beam analysis will be M A plus M B equal to minus 2 A by L. This again being derived from the moment area concept which we have studied in the earlier sections, and M A plus 2 M B equal to minus 6 A x bar by L squared. So, with these two equations, with these two additional equations, because we have additional reactions unknowns M A and M B have to be found. So, we use these two additional equations derived from compatibility conditions. So, M A plus M B equal to minus 2 A by L, and M A plus 2 M B equal to minus 6 A x bar by L squared. And what is this A and what is this x bar? So, in the fixed beam analysis, what they will be doing is, first they will assume a fixed beam as a simply supported beam subjected to given loading, and the bending moment diagram will be drawn. So, we are very familiar in calculating the bending moment of simply supported beams. So, calculate or draw the bending moment diagram. This A represents the area of the free BMD. We call this as free bending moment diagram, free BMD. So, free BMD means treating the given beam as a simply supported beam and drawing the bending moment diagram as the free BMD. So, A is the area of free BMD, A is the area of free BMD, and x bar, area and x bar is the moment of the area about the left end A, moment of area about the left end A. So, that will be x bar. So, x bar is the CG distance of the free BMD with respect to the left end. So, once we know the area and CG distance, then we can easily substitute in these two additional equations, and the two additional unknowns or redundants we call as redundants. Redundants are nothing but the excess reactions. Excess means the excess which cannot be found using the available equations. So, excess equation or excess reactions are called as redundants. So, redundants can be found using this method, and then we have continuous beam. So, as I said, continuous beam of this type to and the only unknown will be the additional unknown will be the moment at B. Once that the moment at B has been found, then we can easily find the reaction at supports using equations of equilibrium, and then we can proceed in finding shear force and bending moment. So, how do we find this MB? So, for finding MB or analysis of continuous beams, we have several methods, namely we have theorem of 3 moments, slope deflection method, moment distribution method. So, we should be in an idea, or we should know what are the methods available for solving indeterminate beams, and in general these methods are classified as 2, that is, one will be force method of analysis and the other will be displacement method of analysis. We will see the basic concept of these 2 methods, and with that we will conclude the session on introduction to indeterminate beams. In the force method, we will be treating the redundant force as the unknown. We will be treating the redundant force as the unknown, and finally, we will be getting the solution using the various theorem of minimum potential energy or virtual work concept. So, the strain energy method is an example of force method. Strain energy method is an example of force method with which we can solve indeterminate beams. And then displacement method of analysis. So, as we have discussed, the slope deflection method, moment distribution method, and we have Canny's method. So, these methods form the displacement method of analysis. So, the basis in displacement method of analysis is we will be treating the rotation, slope or deflection as unknowns. We will be treating the rotation or displacement as the unknowns, and then we will be using the equilibrium equations at every joint, and then we will be arriving at the unknown rotations and we will be solving. So, that concept will be made use of in the slope deflection method and the moment distribution method or Canny's rotation contribution method. So, we have an idea of what is an indeterminate structure, how to find the degree of indeterminacy, and what are the methods available for solving indeterminate beams. So, these things should be had in mind, and we do not involve problems of this type. Only we should be in, at this point we should be in a position to obtain the degree of redundancy of a structure, and we should be in a position to explain what are the various methods available for analysis of indeterminate beams. And we also have the latest or recent methods, we also have the matrix methods of analysis. So, due to the advent or invent of computers, we have matrix methods of analysis for indeterminate beams. So, in the matrix methods, the computations or formulation will be all based on the matrix operations. We will be computing the element stiffness matrix, the global stiffness matrix, and everything will be in matrix formulation, and they will involve the finding the unknown redundant forces. There again we will employ the basic concepts like force method of analysis as well displacement method of analysis. The thing which we need to remember in case of finding the degree of redundancy is number of reactions minus conditions of equilibrium, that will give you the degree of redundancy of an indeterminate structure. And to find degree of indeterminacy in case of trusses and framed structures, that will be a different concept. We will have to see for the internal redundancy also in case of trusses. Say for example, if you have a truss and if you have a support like this, then if you have members, we call as degree of external redundancy and internal redundancy, or externally indeterminate and internally indeterminate likewise. So, if the support external reactions or forces, if the external forces if they are able to solve with the help of static equations of equilibrium, then we say the structure as externally determinate. And if we have excess reactions, as we have seen in the case of propped cantilever, continuous beams and fixed beams, then we say they are externally indeterminate. And in case of trusses like this, we will have additional forces, internal forces, and in addition to that we will have internal forces. For example, say we have for 6 members, the say we need to remove any one of the member and solve. So, that extra internal force will be there. Therefore, the structure will be internally indeterminate. Structures can also be internally indeterminate, and we have various methods of solving internal indeterminacy also, like virtual work method, unit load method, and we can also employ strain energy method for solving problems of this type. So, in this topic we have seen how to apply the Rankine's formula of calculating the critical load of columns, and then we had a brief introduction to indeterminate beams. What is an indeterminate beam? What is degree of redundancy? Examples of determinate beams, examples of indeterminate beams, methods of analysis of indeterminate beams, and what is internal indeterminacy and what is external redundancy. So, with this we conclude, and the questions will be: express the Rankine's formula of calculating crippling load of columns. We have derived we have the Rankine's formula, you need to explain, and then what do you mean by an indeterminate structure, and list the methods of analyzing indeterminate structures. Thank you.